thank you for the introduction and the possibility of giving this talk. So this is going to be, I will talk about a joint work with Serena Di Pierro from University of Western Australia, Luca Rossi, who is now in Rome, and Enrico Valdinoci, who is again in the University of Western Australia. So I will talk about Lotka-Volterra competitive system and a new model that we introduced for competition and war in between two population. And I know that a lot of you are expert in Lotka-Volterra competitive system, but just to have everyone on the same page, I will introduce the topic from very basic stuff. So let's talk about population dynamic. So we study the evolution of a size of a population. For example, if we take just one population, we call U the size of this population. The main idea behind population dynamic is that the number of births, of new births at each time, depend on the size of the population and on the quantity of available resources. And moreover, usually we put some parameter into this equation, in particular the reproduction rate, which is the number of offsprings that each individual of the population have, and the carrying capacity of the environment, which is the number of individuals that the environment can feed with its resources. So this is the basic equation that we have in population dynamic. And you see here the reproduction rate, the size of the population. This term is, so if we fix at 1, the number of available resources of the environment, then resources of all the environment, then the available one are 1 minus the one that are consumed by the population. And here this quantity is rescaled by the number of individuals that the environment can feed. So these equations has a really simple dynamic. So if we start from a positive initial data, we will converge to the value K, so the current capacity of the environment, and otherwise it will be 0 for all time. So when we have two populations, the two populations interact between each other. They can be competitive or collaborative, but we will focus on competitive. So now we have U and V, the two sides of the population. And just to have the idea what happens, now the two populations can compete for their resources. So the term that was 1 minus U over K before, setting all the parameter to 1 just for simplicity, here is 1 minus U minus V. So also the second population consumes the resources that the first population needs. And so here, thanks to this term, these two equations are coupled. So now let's put back all the parameters that we had before. So we had the reproduction rates for the population, the carrying capacity for the population. Moreover, this time we have some competition coefficient, which appear here and here, and they give these competition terms that are the coefficient times U times V for the two population. And these terms tell how much the other population prevents one from the collection of resources, not only by consuming them, but also for some issue of territoriality or of aggressiveness between population. But I want to stress that this term has this probability of meeting, so U times V is the probability that two individuals of different population meet. So this term acts only when the two populations meet each other. And of course, this system has a little bit more complicated dynamic, just for completeness. So there are some cases in where there is a weak competition. So there is a coexistent equilibrium, so the two populations stay alive in the same for all times. Otherwise, sometimes one population prevails and prevails for all initial data. And in other cases, there is the outcome depends on the initial data. So for some initial data, the first population wins, the first population prevails, or for some initial data, the second population prevails. And so this Lotka-Volterra competitive system has a very successful history. People have added the spatial diffusion, and then they have considered strong competition. And for example, later we will hear from Susanna the case of spatial segregation appearing when the strong competition coefficient go to infinity. But all these models rely on the idea that this competition depends on the random probability of meeting between individuals of different populations. What we want to define here is a model for two populations that actually look for conflict with one another. So we call this civil war because the two populations share the environment. But since there are not many data on competition between aggressiveness between different populations, we will derive this model from basic principle rather than from data. So we take into account two rational, two strategies population, and we suppose that the first one attack the second one. For simplicity, we say that the second one just depends from the attack, but it does not attack first. And also for simplicity, we say that the war stops at the extinction of one of the two populations, which is an extremal limit. Usually the war stops when one population is much weaker than the other and surrender. But if we take this much weaker to the limit, we can have this extinction appearing here. And for the moment, we do not take space into account. So we imagine that, for example, the clashes happens in a different environment, so they do not prevent the collection of resources, and we don't take into account the spatial distribution of the two populations. So for having this model, we will need some more parameters. In particular, we will need the aggressiveness of the first population toward the second one. And so you remember before I was saying that in the Lotka-Volterra competitive system, the competition arises from this alpha term that we saw before, and is multiplied by a probability of meeting U times V. Here instead, we have that one population attacks the other. So the probability of having a confrontation, a clash, depends just on the aggressiveness of the attacking population and on its size. So this probability of having a clash will have consequence on other terms. For example, there will be some deaths related to these clashes, and so we will have some extra death term in the equation. And moreover, there are some example of a lack of fertility during war in the literature. So we will also take into account some terms counting for this missing birth that happens during war. So putting all together these, we get this larger system. So here you can recognize the competitive Lotka-Volterra system. And here we have this extra term of death and missing birth that were introduced in the last slide. So this is a very general system, but not very easy to treat. And so we do some very easy assumption. Well, basically we assume that the two populations are of the same species. So we can put that the carrying capacity for the two populations are the same. And also we set the competition coefficient appearing here and here for the collection of resources to 1. A little bit for saying that the individual of the two populations use the same quantity of resources, and also for saying that we are not taking this into account for aggressiveness, but we put all the aggressive behavior in this term A. So we can rescale this system with this assumption, and we get this much easier system, where here we are left with 3 parameters. So the aggressiveness, A, appearing here and here. Then we have the losses that of the first population with respect to the second one. So how many losses the first population get in order to inflict 1 loss to the second population. And the fitness of the second population with respect to the first one. And here we suppose that the fitness might be different between population, maybe because of some cultural difference between each population or some gene variation. So we derive this model basically thinking about human conflict, but it can be applied also to other species, like a chimpanzee tend to have some similar behavior of aggressiveness between population, and also some other social insects, for example, ants tend to, some type of ants tend to attack some other colonies. But it can be used also in other settings, for example, in modeling the behavior of two rival companies. So, for example, if we suppose that U and V are the capital, the money of two rival companies selling the same product, these two companies trying to reinvest their money in order to make a better product and more profit. But we can also think that some company may use an aggressive policy towards another one, for example, releasing false information on the rival company, or even a software virus to damage the product of the other company. And so maybe we can use this model also to analyze this kind of behaviors. So let's now look at what happens with this system. So the most important thing, the most important difference with respect to the classical Lotka-Volterra is that we have this linear term in U appearing in the second equation. This means that 0 is no longer an equilibrium for the second equation, and so the second population may become negative in finite time. So here we see, for example, the projection of a trajectory. So it's quite easy that V becomes negative in finite time. So what we put here is a stopping time. So we say that we stop the dynamic if the second population gets extinct while the first one is still positive. And if this doesn't happen, then the dynamic is well defined for all time with positive solution for both population. So this stopping time is actually quite useful for us because, for example, we can say that the first population wins the war if this time stops in some finite time, and we can call E the set of initial condition for which the stopping time is finite. So here we have that if this happens, the second population gets extinct while the first one is still alive. On the other side, we say that the second population wins if the solution goes to some equilibria 0, 1, which correspond to the asymptotic extinction of the first population and the complete spreading of the second one. And we call B basically the basin of attraction of this equilibria here. So let's look now at the dynamic with the constant parameter to begin with. So we will have two cases. The first case is when A, so the aggressiveness times the losses of the first population is less than 1. In this case, we have 3 equilibria. So here in the picture, we have the phase portrait for here we have the first population, and here we have the second population. So the equilibria that appear are 0, 0, which is unstable. Then we have 0, 1, which is stable, and is the equilibrium for which the second population win. And then we have a saddle point that is here in the middle. And this saddle point has moreover a stable manifold passing through here. And what we see is that this square actually split in the set for which the first population win, the set for which the second population win, and in the middle there is this stable manifold of the saddle point. And so the first population win for the initial points that are in this violet set, which are the points that are below this stable manifold. The other case for the dynamics is when A times C is bigger than 1. In this case, we just have two equilibria. So notice that 0, 1 stayed a stable equilibrium, while the saddle point that we had here actually collapsed with the origin, and now the origin is a saddle point. That will have also the stable manifold that splits the square in the two basin, so in the two sets, the one for which the first population win and the one for which the second population win. All right, so this is the basic dynamic, but now we want to look a little bit further. So we want to understand how the different parameters influence the dynamic and how one of the two populations may win the war by changing its parameter. So for doing so, we sympathize, we take the point of view of one of the two populations. And in particular, we take the point of view of the first population, the bad guys that attack the second population. So we can, why do we do that? Because the first population has this very powerful parameter, the aggressiveness, with which it can influence the dynamics. So from now on, A, the aggressiveness will be the strategy of the first population, and we will allow this strategy to be piecewise continuous with a finite number of discontinuities. So now the question is, if I have an initial condition, can the first population win with this initial condition? So it wins if there exists some strategy with these properties for which it wins. So we take the union of all sets for which the population wins with one strategy, and we call this set V. So in the set V, we have the points for which there exists a strategy for which the first population wins. So now we have some problem in controllability. So the first question is, who is this set V? So we want to understand who are the points for which we can win, and this is a controllability problem. Then we ask if the constants, so if A are constants, are as good as all the strategy to win the war. So this is a question about the function space in which the strategy lies. And moreover, we want to understand how we can construct a winning strategy given an initial position. And then at last, we will think about a minimization problem about how to minimize the duration of the war. And the difficulty here is that the problem is not uncontrollable. And we will not be able to use some variational method, but rather we will use some geometrical feature of the dynamic. So before starting to state the theorems, I will need to show you two different regimes that will help us understand what's going on. So we take two limit cases. So the first limit case is when the aggressiveness, here as a constant, goes to plus infinity. So what happens here is that the set of initial point for which the first population win with a very, very big aggressiveness parameter is a set of points that lays below this straight line. So here all the trajectories of the point have become straight line, and here is our set for which we win. The other limit case is when the aggressiveness tends to 0. It's not equal to 0 because that corresponds to a very different behavior of the system. But when it's very, very close, we have that the trajectory here assumes the shape of some curves. In particular, these curves are power of u times some constant. And so here we can exactly prescribe the border, the boundary of this set E as A goes to 0. So keep in mind with these two behavior. Now we start saying who this set V is, so the set of initial condition for which there exists a winning strategy. So we will have different cases depending on the fitness parameter. So when the fitness parameter is equal to 1, is actually a very simple case, because for all strategies, admissible strategy, we have that the set of points for which we win with that strategy is the same as it happened for here, for A going to infinity. So it's the same for all strategies. So in particular, also the set B, which is the union of this E with A, will be the same set. And it's the set of points that lays below this straight line. So we get here that if the two populations, so if rho is equal to 1, biologically the two populations are indistinguishable. And we have here that then no matter what strategy we use, is the initial condition that determines the outcome of the war. So the strategy is not important. It is different when, for example, rho is less than 1. Then here V is a little bit more complicated, and let's look at the picture to understand it. So here in the picture, I plotted the trajectories for a very small value of the aggressiveness in black, and for a very big value of the aggressiveness in red. And we have that the boundary of the set is follows a trajectory for a very small up to the anti-diagonal of the square, and then follow a trajectory for a very big value of the aggressiveness. And the other case, so for rho bigger than 1, is pretty much the same, but with the two, the two pieces reverted. So first the straight line and then the curve. So now we understood for which point we have we can have victory, and for which point we cannot have victory. The next question is how we can get this victory. So we ask if the constants, which are a very small subset of all piecewise continuous functions, are good enough to get this victory. Well, we saw that for rho equal to 1, all the strategies were the same, so also constants work. But for when rho is different than 1, then there are points in V for which no constant strategy works. And exactly, there are a small piece here for which if we choose an aggressiveness which is too small, then we will follow the black trajectory and we will be over the boundary of this set, and then we will eventually hit this red line and go to 0, 1. On the other side, if we take a value of the aggressiveness that is too big, then we'll follow the red lines. And so we'll be inside the set for a long time, but then eventually we will go out and again hit this red line and go to 0, 1. So for these points, we need some other type of strategy. And what we decide to do is to construct a piecewise constant strategies with just one jump. So it's still a set that is a little bit bigger than the constant, but not as wide as all the piecewise continuous function. And we can prove that for all points in V, the first population can win with this heaviside strategy. So this kind of strategies that take one value in an interval of time and another value in the rest of the time, in the control community, they are also called sometimes bang-bang. So the take-home message is that we can win the war with a bang-bang strategy. So a natural question that arises is also what happens if instead of taking all the possible piecewise continuous function, we just take the one that are bounded between two values, for example, small m and big M. And notice that here we allowed small m to be also 0 and big M to be also infinity. So this is a smaller set with respect to the set A. And will this affect the outcome of the war? Well, actually, yes, we can show that the victory, the points for which we can win using just bounded strategy is strictly smaller than the set for which we can win using all the piecewise continuous strategy. So we have lost some points for which we could win the war with the very big value of the aggressiveness, and now we don't. And so the last thing that I want to present is a minimization problem linked to this system. So now that we have the points for which we know that we can win the war with some strategy, also we can show for which point we can win with a bounded strategy. We ask ourselves, among all the possible strategies that allows us to win, which is the one that minimizes the duration of the war, that minimizes time, the stopping time, TS, that we saw at the beginning of the talk. And so now everything should work because we have a problem with the functional, and we can use the Pontryagin maximum principle to do our minimization. But actually, the Pontryagin maximum principle this time tells us something quite strange. So if we want to minimize the duration of the war among all the bounded strategy with some bound and small m and big M, what we get is that the minimizing strategies can take the value small m and big M as we were expecting, but also some other value, which this S is a curve which is called a singular arc. So it's not the smallest value and not the biggest value as we would expect when we look for abandoned strategies, but there is also this part here. And so we ask ourselves, is this really possible, or is just that the Pontryagin maximum principle is not strong enough to solve this problem? So what we do is that we try to use some software, some optimization software. We use IPOP, and we looked at what IPOP was saying about time minimizing strategy. So here you can see in blue, it's plotted the actual minimizing strategy, and in red it's plotted the singular arc here. So here, if we look at this picture from very far, it seems that the minimizing strategy is just flat, and then it bumps at the maximum value at the end. But actually, if you look a little bit closer, we see that this piece here is not really flat. In fact, this piece here is a singular arc, which is different from 0, that was said to be the minimum allowed for the strategy. So it actually happened that this singular arc appear in a minimizing strategy, in a time minimizing strategy. So this also proves how rich this problem is. So these were the questions that I wanted to answer. And now I just spend the last minutes talking about other possible questions that may arise in this topic. So, for example, one could ask which is the strategies that leads to the maximal population size at the end of the war, maybe among the or possible strategy. And another model that we take into account and we are looking at is what happens if the two populations lives in different territories. So the only difference in the system is that here, in the term of the collection of resources, these two terms are different. So here you just have the influence of the population, the first population, and here you just have the influence of the second population. And surprisingly, what happens here is that more equilibrium appear, and you have even more bifurcation appearing. And we are still working on this system. And to take this system a little further, what one could think is a model of space invasion. So imagine that we have two populations, one living in, for example, in dimension 1 in an interval from 0 to lambda, and the other one is living in the adjacent interval from lambda to 1, for example. These two populations have their own dynamics inside their territories, but they interact at the boundary with these flashes. So the bound of this interval shifts according to the pressure on the other side given by the two populations. And if here the two population just annihilates on the moving boundary, and we would like to know what happens and how the two population, one of the two population, can influence this dynamic by controlling an aggressiveness parameter. So this was pretty much all I wanted to say, and I thank you very much for your attention.